Okay, so we don't have any homeworks due today, and I don't have any homeworks back for you, so we'll just forge ahead. Actually, we have to go through a lot of material today. I want to show you how to do a machine language, write your first machine language program. So we'll have a demo near the end of the lecture. Now, at the end of the class last time, we described how the load instruction works. Now, what level of abstraction are we working in here?
Instruction set.
Instruction set architecture, ISA level 3. And so these instructions that we are learning, the reason it's called the instruction set architecture level is because all central processing units have an instruction set that's wired into them. The electronics, these instructions are wired into the electronics of the CPU. Okay, so this is definitely, when these instructions execute, they are executing in hardware. And all of the, the description of the 4 parts of the computer, all of that is hardware. So this is all electronic circuitry. And do you remember what the load instruction did? Or what the load instruction does?
It loads one word from memory. Oh.
Into register R. And we had this example. We were finishing this up at the end of class last time. Now, do you remember how this example worked? First of all, I assume everybody understands now how to decode an instruction. So in this particular example, the instruction is in hex is C1004A. So if I give you, in the homework problem, that gives you like an instruction and it gives it to you in hex, so the first thing you do is you expand it out into binary and then you identify the opcode with the table, and if depending on if there's an R field and an AAA field, you figure out that. And so when we decode C1004A, we see that the C is 1100 and the 1 is 0001, and we notice, and that tells us, the 1100 tells us that it is the load instruction, and the 0 in the R field tells us that what is being affected?
The accumulator.
The accumulator, as opposed to the index register, which would be affected if it were 1. Right? And now the AAA, now actually we are going to have some, yeah.
Does the load instruction always have the RAAA?
Yes.
Okay.
Yes.
So you just know that it is an RAAA?
Yes, yes. Okay, now there is something else that we kind of glossed over here last time that I want to emphasize. What this instruction is doing is direct addressing. Okay, now do you remember how many, so that AAA field, how many addressing modes are there altogether?
8.
There are 8. And so this direct addressing is the second one, right? Because it's, in the slide there, it's 001. So here is how direct addressing works. The way direct addressing works is like this. OPRND equals mem OPRND SPEC. Now, so here is the meaning of direct addressing. Now, the reason we use this notation, what does this notation look like? This square bracket in C++, what would this? It's like an array. And so what you should do is you should think of main memory as an array of bytes. And do you remember how we said each byte has an address? So you can think of the address as being the what? The index of the array. Do you see what I mean? It's like a big hardware array in your computer, and the address is the index. And remember, what did we say the index, what was the range of the index? Well, the smallest one was what? 0, 0, 0, 0, and the largest one was what? 64,000, 64K. Yeah? So, and now, what does this OPRND stand for? Operand. And what does this OPRND SPEC stand for? Operand specifier. And remember, in the instruction, remember over here, remember what part is of the instruction is the operand specifier? It's the what?
The second 2 bytes.
Yeah, the second 2 bytes, the 004A. So what this direct addressing is telling us is that the operand is mem sub operand specifier. So what this says is that the operand, how do you say this in English? The operand specifier is the address in memory of where the operand is. Do you see what I mean?
Yes.
So the operand specifier, is the address in memory of the operand. All right? So anytime you have direct addressing, this is the relationship that this is what it is. The operand specifier. So therefore, when we see how this load instruction executes, what it does is it goes to, because the operand specifier is 004A, it goes to memory location 004A, and it takes the 2 bytes. Now I've shown the 2 bytes there, 92EF. What's the address of the 92?
004A.
But then what's the address of the EF?
004B.
So do you see that the address that it's giving is the address of the first byte in memory. But it takes 2 of those bytes. It takes that one and the one next to it. One right after it. Are you with me? And it goes over the bus up into the accumulator. Because how many bytes are in the accumulator? 2 bytes. So does everybody see how that worked? Okay. Now, the next instruction is the store instruction. Well, if we have an instruction that takes information from memory to the CPU, we've got to have an instruction that does what? Goes from the CPU to memory. So that's the store instruction. So is everybody with me on this? So the instruction specifier is 1110, and again, it's an R bit, the register specifier, and then an AAA. So this stores, and this does the opposite. And so here's an example of how that instruction works, okay, in figure 4.13, 4.12 and 4.13. So if the instruction is E9004A, the E is 1110, that's the opcode for the store, and you see it does just the opposite. Does everybody see how this works? Only this time now it's E9004A. So what is 9 in binary? 100. So now this is telling us that there's a 1 in the R field. So now instead of going from the accumulator to memory, it's going from the what? Index register to memory. That's because R was 1 in this case. Does everybody see how that worked? If this had been 0, it would have taken it from the accumulator to memory. And similarly for the load. Is everybody with me on this? And what happens to the original content of 004A?
Gone.
It's gone. And furthermore, what's the address of the BC here afterwards?
004B.
Yeah, 004B. It's the next one. Is everyone with me on this? Because the index register is 2 bytes.
Can you go back a slide for just 1 second?
Sure.
Perfect.
Got it? And notice that there are no status bits are affected by this instruction, as in contrast to the previous one. Now, how do you add? How do you do an addition in PEP 8? Well, with the what? With the add instruction. Now, do you see? So it has an instruction specifier 0111, and then it's RAAA. And this adds 1 word from memory to register R, and it puts it in register R. Is this clear? Mm-hmm. So you see what is this specification down here called?
RTL.
RTL, and what does RTL stand for?
Register translation language?
No, you're close, but no cigar.
I know it's RTL. That's all.
Yeah, okay, RTL. So someone else say what's the RT?
Register transfer language.
It's a register transfer language, okay? And so what is and what is the semicolon?
Sequential.
Sequential. So first what happens? The register R gets what?
R plus operand.
R plus the operand. So it takes whatever's in register R and whatever the operand is, it adds them together and puts the result in register R. Are you with me? So that's why it's called an accumulator. Well, if it's the accumulator, if R is 0, it's the accumulator. So it like accumulates the sum in there, right? And then N it affects the NZVC bits as usual. And here is an example. So now, can we do this in our head? Can we do this addition in our head? What is FFF9? You see that before at location 004A? What is FFF9? 11111.
001.
1001. Yeah, and that's a negative number, isn't it? Okay. So and what is that number anyway?
Huge.
A lot.
No, it's not a lot. Come on, you can't do this. You can't figure this out in your head.
10 plus
If it's negative,
16
it's
times
only.
15.
No. It's a negative number. You look at the what places. You look at which places.
Oh, so it's like
You look at the zeros.
-7.
It's -7.
-7.
4 plus 2, the zero's at the first and the fourth place and the twos place. That's 6. One more is 7, so that's -7. And then what's in the index register? The initial value of the index register.
Oh, it's FFFE.
No. In the index register before.
FFFE.
Oh, 0005.
5.
There it is. Okay.
So are you with me?
Literally.
So this is adding what? Negative
7 and 5.
-7 and 5, and notice that the R is 1, okay? So it's going to go from that memory location, and it's going to add that to there, and so negative, what do we say? -7 and 5 is what?
-2.
And is this -2? It is -2. Everybody with me on this? Okay, so here's the subtract instruction. So subtract instruction works just like the add instruction. Actually, what happens is, those of you who are in the computer organization class, we will actually see that, guess how the hardware does a subtract?
Adding negatives?
Yes, what it does is it adds the negative. So in the hardware, it actually inverts and adds 1 and then adds it, yeah. That's how it actually does it. So here's an example of the subtract, and now what are we doing? Now what are we subtract? Oh, this time R is 0. The R field is 0. Okay, so now what are we doing? We're taking the accumulator is
Subtracting 3.
now which one are we subtracting? Are we doing 3 minus 9 or 9 minus 3? Which one is it? Here, let's go back and look at the RTL.
It's from memory.
Its register gets what?
Register minus.
Register minus the operand. So what's it doing here?
3 minus 9.
3 minus 9, which is what?
-6.
-6. And is that -6? What's A?
10.
1. No, I mean in binary.
It's 1 0 1 0.
Oh, right.
What is it? 1.
1 0. Yeah.
1 0 1.
0 1.
So it's
No, 1010.
1 0. Is this A? 1 0 1 0?
Yes.
And so this would be what? This would be what? 1 plus 4 is 5, plus another one is 6.
It's -6.
So FFFA is -6. And is that right? 3 minus 9 is -6. Okay? Are we good? Here is the AND instruction. So what does this do? Look what does it do? R and the operand. Okay, so, and it's bitwise AND. Okay, so can we see, and the opcode is 1001, and they got 1 for the register field, so we're going to AND the content of memory with the index register because R is 1. And notice all of the, again, what's the address AAA field?
001.
001, so that means what? Direct addressing. So all of these examples that I'm giving you for your exercise are all direct addressing, because that's the only one that we're learning so far.
Okay.
It'll be different when we learn if the addressing mode is different. Okay, we'll learn those later. Okay, and so how do you can see, check out what we're ANDing. This is an interesting use of a mask. Look, what's at memory location 004A in the beginning?
00FF.
00FF. So that's what? 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 1, 1, 1, 1. Okay, so now, when you AND 0 with anything, what do you get?
Here.
0.
And when you AND 1 with anything, what do you get?
0.
No. When you AND 1 with anything, what do you get?
Get anything.
You get that, you get what it is.
Yeah.
So what is that doing? Well, if you AND that, what is that doing? That's wiping out the what?
The first bit.
The 5D
And keeping the
and keeping the C3. Do you see how it did that?
Yeah, that's cool.
Is that, yeah, that's called that's called masking out. You mask out the, yeah? You mask out that if you ever need to set something to 0 and keep something else the same, you bitwise AND it with the AND instruction. Are we good? Here's the OR instruction. Okay, so the instruction specifier is 1010, again RAAA. And what does it do? What is the
R gets R or operand.
R gets R or the operand? Okay, and so here's, oh, by the way, oh, no, I was going to say something that wasn't true, but, oh, I don't have a,
Description here.
oh, I don't have the decoded thing, but, I mean, we see how to do it, right? Now what happens, hold on, now what happens if it, in memory is 00FF? But now what's going to happen when if you OR 0 with anything, what do?
You get the other thing.
You keep it. But then what happens if you OR it with 1?
You get 1.
It's 1. So now that 5DC3 turns into what? 5DFF. So does everybody see how that works? So anytime you want to force a bit to be 1, what do?
You or it.
You OR it with 1. Anytime you want a bit to be, anytime you want to keep all the other bits the same and you want to force a bit to be 1, you OR it with that. All right? And anytime you want to clear a bit to be 0, what do? You AND it with 0. So regardless of what it is, yeah, if you AND it with 0, it makes it 0. If you OR it with 1, it makes it 1.
Is the instruction specifier 1010?
It's A9.
It's 1010.
Is that right? Yeah, 1010. There it is, instruction specifier, right? And that's A. That's the hex letter A. Okay, right? Okay, and now comes our first unary. Oh no, it's not our first unary. Stop was unary. Here's another unary. Here's our second unary instruction. The not instruction. Now look, because it's unary, there's no what?
Operand specifier?
Yeah, there's no operand specifier, right?
Or addressing.
And there's no addressing mode, right? Now, do you see why the not instruction has no addressing mode? Because what it does is what? It's not negation isn't a binary operator.
Yeah, it only takes it the one.
It's a unary prefix, yeah. So it only takes the one thing. So the only thing it needs is what? An R field, okay?
To see where it's getting
To see which register it's going to not, to negate, to do the not on.
And
Are
it
you with
just
me?
negates that register.
No, it doesn't negate it. It knots it. I mean, by negate, we usually use that word for
Doing
negate, making negative.
Taking the
2's complement, right. Okay, so you got to be careful of the way you. So it's the bitwise not operator on register R. Each 0 changed to 1, each 1 changed to 0. So there's the RTL. Are we good? Which stands for?
Register transfer language.
Register transfer language. And here's an example. So if the accumulator is 0003 before, and we execute the 18 instruction. So what is 18 in hex? 0001 1000, which means that the R field is 0. Is everybody good? And then if you look up the opcode 00011100, that's the not. R is 0. That means we're going to not what's in the accumulator. So what is that in binary? 0000, 0000, 0000, 0011. So you flip them all around, it's FFFC.
It's -4.
Yeah, which will be -4. It will be 3 plus 1 is 4 and -4, right? And what is negate? It's also unary. Okay, it's negate. You take the 2's complement, so R gets -R. And so it, flips the bits and adds 1. Okay. So here's an example. Negate the accumulator. 0003, now what would it, afterwards, what will it be?
FFFD.
FFFD, because
That's -3.
that's, yeah, that's -3. Is that right?
There's
1110, yeah, to the previous, yeah. Is everybody good? Now comes one that has the potential for much confusion. So I would like to I would like to emphasize a subtle problem or issue here that you really have to be aware of. This next instruction, these next two instructions are called byte instructions. Now, do you remember what the load instruction does?
Yeah.
What does it do?
It takes something from
Memory
to
and puts it
register
into register R in the CPU.
Right.
And how many bytes does it take?
Byte.
2.
It takes 2 bytes. And why does it take 2 bytes? Because it takes 2 bytes to fill that register.
Right.
So the address that you give it is the address of the byte plus one more.
Byte after.
The byte after that has address plus 1. Are you with me? And those 2 bytes go into either the accumulator or the index register. Are you with me?
Yes.
Now, sometimes you don't want to put 2 bytes into the accumulator. Sometimes you only want to put what? 1 byte into the accumulator. Like, for instance, if it's a character.
Right.
Are you with me? Instead of an integer. Yeah?
Or a word.
Hmm?
Or a word. Words are 2 bytes.
No, I'm saying sometimes you want to just put 1 byte in there. All right? And so this instruction is called the load byte instruction. Now, and this has the potential for some confusion because look, if we're going to load a byte into a register, the question is, which part of the register are we going to load it into? Are we going to load it into the most significant byte or the least significant byte? Now, can you tell from the RTL specification which part of the register it goes into? Is it the most significant or the least significant? It's the least significant. Not only that, but there is no, when it goes to memory, here, let me write this down a fact. Let me write down a fact here about memory. Memory is byte addressable. I hope I spelled addressable correctly there. I don't have a little spell check on my board. Memory is byte addressable. Now, what does that mean? That means every byte in memory has its own what? Address. Now, I'm here to tell you that this is the way the industry has kind of like converged. But in the early days of computing, this was not the case. In some early machines, there were like, you wouldn't believe it, some machines had like 30 bits per cell in main memory. Some had 16, you know. And it took a number of generations of CPU design for the manufacturers to all converge on the fact, on organizing memory in 8-bit byte cells. But it was not always this way. It has not always been this way. All right? But now, I mean, you know, when you first build, you know, when you invent something new, or like when you write new software, sometimes you have all this flexibility and you have all these decisions to make, and sometimes it's not obvious what the best decision is. Only over time do you. In fact, I'll tell you, this 2's complement binary representation, that's not the only way to store negative numbers. There are different schemes for storing negative numbers. negative integers. And they didn't, and the computers didn't all use this 2's complement representation. It's only after the first, a couple or 3 generations of CPU design, then people said, you know, this has advantage this way, the advantage this way, and everybody kind of said, you know, after we've used it for a while, we see now that these advantages are better than these other advantages, and they kind of like converged on the standard. You see what I mean? But there's nothing magic about the way all of these things are represented, and there's nothing magic about the way memory is byte addressable. In the early days, it wasn't. So now look. So the point is that when you have the load instruction, which bytes get loaded from memory into the CPU? Well, it's the byte specified by the operand specifier and one address and the one next to it. But in this case, which one gets put in? It's the byte specified by the operand specifier, but it gets put in the No. It gets put in the
Right half?
in the least significant byte
Okay.
of the register.
The address is of the left byte, isn't it?
No. It's the address of the byte, because memory is byte addressable. So there is no left or right. You can kind of think of it that way. But you should think of memory as being byte addressable. That's why I'm emphasizing
So
this.
the address that's given is the actual address of the...
Is the actual address of the byte. Is the actual address of the byte that gets transferred from memory. But when it gets put in the accumulator, since the accumulator is 2 bytes, it goes in the right half.
Okay.
It goes in the right. And what happens to the left half, by the way, of the accumulator? What happens to the left half of the accumulator?
Set to 0?
No.
It's left?
It doesn't say that. If it said that, look, if it said that, what would it say? The RTL would say what?
0 through 7.
It would say R0.7 gets 0. But it doesn't say that, so that means it's left alone. Now, is that clear? Okay, so now here's an example. So here we have D1004A. If you look at D, that's 1101. That's the opcode for the store byte instruction. Sorry, for the load byte instruction. Are you with me? Now look at in the before scenario. Look at what's in the accumulator. What's in the accumulator?
0360.
036D. And at memory location 004A, there's a 92. Are you with me? So, and so afterwards what happens is that 92 goes in the right half of the accumulator, and that 03 stays unchanged. Now, does everybody see that? This is a crucial, people get confused about this all the time. And I predict that you won't get 100%. There's an exercise for next time, and I predict that not everyone's going to get this right. If you do, it'll be a pleasant surprise for me.
Is there a way to force it to load to the more significant byte?
No. If you want it to go to the other side, what you have to do is you have to put it in the right side, and then you have to shift it to the left. Yeah. So there are shift
Can't you
instructions.
just do like the regular load instruction and then do...
Well, actually, you could do that, but then to do that, you could do that. You could use, and then mask the other one out, or somehow if you want it. Yeah. Okay. Now, if there is a load byte instruction that goes from memory to the CPU, there's also a what? A store byte. All right. And you see what it does here? Byte operand gets R 8.15. Is everybody clear? So here is the store byte. Okay. And so if in the accumulator there's a 036D, and in memory at 004A there's a 92, then if you do store byte, that 92 changes to 6D, because that's the right half of the accumulator. Does everybody see how that works? These figures are all in the book. Okay. Now we have the next two instructions are character input and character output. So the character input instruction is, now, you guys, what are the 4 parts of a computer?
Input,
CPU,
CPU, main memory.
An output. Now, what do you suppose, now, how does information flow with an input instruction?
Onto the bus.
From where? Aha.
You said input?
Yeah, this is the character input. So where does it come from?
From the
user.
input.
It comes from the input device. It comes from the input device. Are you with me? Input device could be a keyboard. Yeah? Whatever. Could be a file. Is everybody clear? Okay. Whatever. Input. And furthermore, it comes 1 character at a time. And so what it does is it stores 1 ASCII byte from the input device. And where does it go? Does it go to the CPU?
No, it's memory.
No, it goes to memory. And so is this a unary or a non-unary instruction?
Non-unary.
It's non-unary because the operand specifier tells it where it goes. Is everybody clear? So now, this example that we have here now looks, we have to show not only the CPU and mem, we have to show what? The input device. See, so if there's a W in the file, and that's the next thing to be input, and you do the character input, 49004A, then it's 1 byte. So the memory location 004A has a 92 in it. Well, the W, now what is this 57?
That's the
It's not
code.
ASCII.
That's the hex code for W. So if you look up in the hex chart, that's how we denote it.
So the dashed arrows though mean that the CPU
Is controlling that.
Also.
Yeah. Yeah, because, you know, remember how I always say, we've always said that the instruction set is wired into the CPU? Well, this character input is one of the instructions that's wired into the CPU, so the CPU is controlling that flow, that data flow. Is everybody clear? And if there's a character input instruction, there must be a what?
Character output.
Character output. So here's a character output instruction, and where does it go? From where to where?
Byte operate from memory to output.
Yeah, from memory to the output. So here's a picture. So now if you have in memory 48 at 004A, and you do a 51004A, that'll be direct addressing again, and whoosh, that 48 will go to, now wait a minute, that's a 48 in hex. So that's the ASCII value for H. All right. Now we have all those instructions under our belt, and now what we want to do is we want to see how these instructions actually get executed in sequence to execute a program. All right, now, I'm sure my cameraman remembers this. Every once in a while, there's a slide that you have to memorize.
There's a lot of those in this.
There's a lot of those in this one, all right. Yeah. You're right. What happens when you call a function? Storage for that, storage, What are the 7 levels? Application, I say 3. What's the von Neumann execution cycle? Here you go. What is it? Fetch,
Instruction.
decode, increment, execute, repeat. Okay, so you can tattoo that onto your forehead. So when you get up in the morning and you go into the bathroom, you'll see fetch, decode, increment, execute, repeat. Now let's take a look at each one of these in turn. When we say fetch, what do we mean? Fetch what?
Instruction.
Fetch an instruction. And where are these instructions stored, do you think?
CPU.
No. They're not stored in the CPU, actually. That was a good try. You might think it is. I mean, that would be a good guess. Yeah, the instructions are stored in main memory. Are you with me?
And the program counter?
No. The program counter is the address in main memory of where the instructions are stored.
Okay.
Are you with me? Is everybody? Yeah, I see I didn't say what had to happen before we do the von Neumann cycle. What has to happen is, before you do the von Neumann cycle, you have to load the instructions into memory.
Okay.
And the operating system does that.
Okay.
Is everybody clear? Okay, so that's how they get there. So we assume that the instructions have been loaded into main memory in binary, like we've seen how they are. Are you with me? And then what happens is the von Neumann execution cycle, this is an endless loop that's wired into the CPU. Because when it says repeat, what does that mean? Fetch, yeah, decode, increment, execute, and then repeat, boom, 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 repeat over and over. So it's like an endless loop wired into the CPU. Now look at what it said. So the first one is fetch. Now what does it fetch? It fetches an instruction. And how does it know where in memory to go fetch that instruction?
Is that sub-PC?
That's sub-PC. So the program counter has the address of the instruction in memory of where to fetch from. Are you with me? And then once it fetches that, where does it brings it from where to where?
Main memory to the CPU.
From main memory to the CPU. And which register, have you memorized what the registers in the CPU are?
Oh boy.
Which register in the CPU does it put that instruction in?
Index.
No,
Accumulate.
no.
The instruction.
Instruction what?
I don't know.
Start.
The instruction register. Do you remember one of those registers in the CPU was the instruction register?
That was close.
Yes.
Okay, so IR. So it goes from memory into the IR. Does everybody visualize that?
Okay.
Can you visualize that?
Which is what we've been working with this whole time with the operand specifier.
Yeah, and all that. Yeah. In the IR, okay? And then the second thing is what? Decode the instruction fetch. Now, do you know what you remember how we decoded? How did we decode manually? We'd look at the 100, we look at this table, we figure out what it is, then we figure out what's the R field, we figure out what the AAA field, or if it has an AA field, or if it's unary, and so it's figuring that stuff all out. All that stuff, the electronics figures that stuff out. And it looks at that bit pattern in the IR and figures out what the instruction is. Are you with me? Then what it does is it increments the program counter. Now, why do you suppose it increments the program counter?
So it doesn't repeat the same program every.
Yeah, it makes the program counter increase so that the next time you go through the loop, it will take what?
Different instruction.
The instruction right next to the one it just fetched. So you see they're stored next to each other in memory. And you have to increase the program counter by 1 so that it will get the next one. Does everybody see that? Are you with me?
So does it eventually just start over?
Well, it will eventually, until it gets to stop.
But isn't there not really a stop?
Well, there's not really a stop. So it will eventually, it gets done, and then it will go back to the operating system, and the operating system will take over, and all that time the von Neumann cycle is going over and over and over. Okay? All right? And then after it increments the PC, it executes the instruction fetch. Now, here's a crucial detail. If we are executing the instruction fetched, here's my question. Are we executing the instruction that is the instruction where the PC?
No. Program counter is already above 1.
Yeah. The answer. So the answer. You are correct. The answer is no. Because what did we do?
We already fetched the instruction.
We fetched the instruction, then we incremented the program counter, then we're executing the instruction fetched. So we're not actually executing the instruction that the PC is pointing to, because it's pointing to the one that will be executed next. Are you with me?
Is that so that as the instruction's being executed, it can be interleaved with fetching it?
You have asked a really good question, and I'm going to have to postpone the answer to that until later, because it has to do with the branching instructions. And there's a good reason why it's like this. But it's very close, not quite, to what you said. And then we repeat over and over again, right? Okay, so now here is a more detailed, in figure 4.30, I have a more detailed description of the von Neumann cycle. And notice that there's some initialization here. So the first thing you have to do is you have to load the machine language program, and then you have to initialize the PC and the SP. Now, I'll tell you right off the bat that in the PEP8 simulator, what we do is we load the instruction starting at 0000. That's where the programs go. Are you with me? So therefore, what do we have to initialize PC to be?
000.
0000. Because we want to start fetching it at the beginning of memory. Are you with me? Now, in a real system, it's more complicated. It gets loaded at a certain place in memory, but you got to set the program counter to the first one every time, yeah, regardless of where it's put. All right, is everybody good? Okay, and now here is something, I'm going to skip over this, and now we're going to actually execute a program. Now, I have here in figure 4.32 a machine language program written in binary. Now look here, you guys. The address starts at 0000, right? And there's a machine language instruction 0101 0001 000000000000001111. Now, if you look up that, that's what it is in binary. If you write, I have written it also in hex here and with some comments. Now, if you look up that first instruction, that 5-1, that turns out to be a character output instruction. Are you with me? Now, do you see that those bits, do you see that the byte, it's 510007, and then at the next address it's what? 0003, so that's the third, you see why how the address corresponds to that? And then 510008, and that's another character output instruction. And then do you see that at 0006, that's the 00, so that's the stop instruction. And now look, at 0007 there's a 48 in hex. And at 0008 there's a 69. Are you with me? Now what does that first character output instruction do? It's character output from address what? 0007. So it goes down to 007 and takes that 48, and that 48 comes out as the letter H. And then the second instruction, it says output from 0008, so it goes down to 008, it takes that bit pattern 69, interprets that as an ASCII character, and outputs the letter I. And then the next instruction is stop, so the instruction stops. Are you with me? And so the program stops. All right. Does everybody see how that worked?
Yes.
Now what I'm going to do is I'm going to show you how to actually run this on the PEP 8 simulator. So we're going to do a demo. But now in order to do this, can somebody either write down or memorize this sequence of bits? 510007, 510008, 004869.
Got it.
Got it? Because we're going to need to know how to do this. So we're going to, okay? Now, so here we go. All right. So first we will,
Do we just have to download one thing for the PEP 8?
yeah, it's on the link there. Okay, so here's the demo. What you will do is the web page will show you, will give you the link for how to, of what to download. So here is the PEP 8 virtual machine, right? So here's the screen. Now, one thing that you will want to do is, I see that our resolution is such that all of the tools don't show up here. So if we want, there's another little panel that will show up when you do it. You can see not only the code and the CPU, but you can also see what's in memory. All right? So that's under view. You can, or wait, is that under view? Yeah, here here. See, you can do code only. You can view the code only, or you can view the code and the CPU, or you can view the code, the CPU, and memory. Looks like my resizing thing isn't quite. All right, is everybody with me on this? Now, do you see this memory dump here? 00000008. You see here's 1 byte, 2 bytes, 3 bytes, 4 bytes, 5, 6, and 7, right? 0, 1, 2, 3, 4, 5, 6, 7. Then this is 8, 9, 10, 8, 9, A, B, C, D, E, F, 1, 0, 1, 1. So you can read that memory dump, right? That shows you what's in memory. Now, what did you say? What did we say the program was? Did you that in hex? Now watch this carefully. 5-1. Now this is very important. Space, a single space. Then what? 0, 0, single space.
So you're separating the bytes.
Yes, and it's got to be exactly one space. It's very picky. And then what's the next one?
07.
0, 7. Now, I could put a space here and keep going, Or I could just put one return. But if you put a return, you can't have any trailing space. Are you with me? Now, what was the next instruction? 5-1 space 0-0 space 0-8. Return, no trailing space. What was the next one? 0-0. That was the stop. And then what did we have?
We had the two locations.
4-8.
4-8. And now I can just put either space or return, right?
6-9.
And then 6-9. And now comes a very important thing. The loader requires a sentinel. The sentinel, so we put space, and now where we would put the next byte, we put lowercase zz. Are you with me? Is everybody clear? Did you see how I did that? And now notice that's the object code pane. This is not in the source code. This is in the object code. Because we're writing in machine language, okay? So that's here in the object code pane. Now, you guys, what we do is we come up here to build. Now you see here we have input and output. Now we come up here to build, and what's the first thing we have to do before we can run this program? Look, see the options here on this menu? No, because we're not writing in assembly language, we're writing in machine language. We have to load it. So we come down here and we do load. Now watch what happens to the memory dump pane when I do load. You ready for this? Boom. Did you see that?
Yeah.
Now that's 510007, 510008, 0048. And where's the 51? It's at 0000. Okay, 1, 2, 3, 4, 5, 6, 7, and then 8, 9, A, B, C, right? Does everybody see? So it took what was over here and it put it in memory, just one right after the other, starting at 00. Are you with me?
Can you scroll to the right on memory dump and just see what? Okay. So
Yeah, now the dots, you know, if it's a printable ASCII character, it'll print it out. But if it's not printable, it'll just show with a dot. Okay, so is everybody?
And this is all done in hex.
And it's all done in hex. All right? And now, after we've done that, now what do we do? Looks like we have a little drawing problem here. So now under build, we did load, and now we do. Now watch what are you supposed to happen when we do execute?
it'll be in the output.
Boom.
Right.
Is that cool?
Mm-hmm.
Now, if you want to single step through it, watch this. Under build, we can say start debugging object.
Okay.
So if you do start debugging object, watch what happens. Now, you see in memory dump, it shows, oh, we're about to execute this, right? And here there's a single step button, and here in the CPU is a picture of the accumulator, the index register, the stack pointer, the program counter, etc. Get these. Wait, here, let me try to get this.
You're all right. Don't worry.
He doesn't like that.
We can read it.
Yeah, okay. My resolution is not as good on this
Screen.
projector. Okay. So now look, this is the program counter, right? This is 0x means hexadecimal. So the program counter is at 0000. So when I single step, watch what happens. Boom. So see it now the
Operand specifier.
the operand. Yeah, this is the operand, the instruction specifier. We just did a character output using direct addressing from 0007, and that was the 48 there, and that's how the H came out, you see? Mm-hmm. And then over here it shows you which one's going to be next. And so you single step through, there's the I, and now notice now that the program counter is at 0x0006, hexadecimal 0006, and then one more, that's the stop. Okay, so that's the demo, and so now let's think about what you have to do for your homework assignment. What you have to do is write a program in machine language that outputs what? Have you looked it up yet? Mm-hmm. Your first name.
Cool.
But I forbid you to use a 2-digit abbreviation for your name. You know,
'Cause you
do
want to
not.
have a space?
No, because I want you got to have more than 2 characters in the output. Because look, how are you going to modify this program? Instead of just having 1 character output, 2 character outputs, like if yours is like 3 letters, boom, or 4 or 6,
Yeah.
you know, or your whole name if you want.
Okay.
But then what's going to happen? After those output instructions, you're going to have what? Stop, but then after the stop, what are you going to have?
The letters.
You're going to have the ASCII, you're going to have to look up the values of the letters. Now, where will they be?
Further down in memory.
Further down in memory. So that means you're going to have to go back up and make sure that the what?
The operand specifier.
That the operand specifier is the address of where they go. But that's going to depend on how many instructions there are.
Perfect. Good deal.
Now, but you can figure that out,
Yes.
right?
We can do that.
Good deal. See you next time.